This is recorded, right?
Yeah, yeah, yeah.
Yeah.
This will get recorded.
Yeah. I think people can access it later.
So, welcome everyone. Welcome to AstroTalk number 49. Today we have Dr. Swarnim Shirke, who is PhD in Astrophysics from IUCAA. This is basically in continuation to earlier talk on stellar zoo on 9th May. Dr. Swarnim
Okay.
Shirke.
Yes. Thank you for the introduction. I'll share my screen.
Yeah.
Uh, so is my screen visible?
Yes, we can see the screen. If you can make it full screen, it will be great.
It is full screen.
Okay, please take over. Thank
Yeah.
you.
Okay. Yes. So good evening, everyone. So today I'll be talking about a particular class of stars. It's not a particular star, but it is a bunch of stars that comes under the umbrella term of compact stars. So there are multiple different types of stars that come under this category, and I chose this topic because yeah, it is in continuation with the earlier talk which my sister gave, the stellar zoo, which covered all different stars that you can see in the night sky. So this is one of the slides from her presentation. So out of this, I'm going on a particular subset of stars, which are very interesting and very rich in science and physics in general. So to talk about stars, this is one of the standard ways to describe or classify different stars. This is called as the HR diagram. So here it is usually plotted like for every star, we can make a measurement of the luminosity and also of the temperature if you have the spectra of it. So usually this is plotted along this two axis graph, and it's called the HR diagram. And the main, you see a dense region that is called as the main sequence. So this is where most of the our usual stars, even the sun, our own star, lies somewhere in the middle of this. So these are our usual class of stars. Uh, from this, so this is where our different stars, and but their stars are not they're transient objects, so they are not like in equilibrium. They are constantly moving, and they leave this main sequence eventually. So this evolution is described by stellar evolution. This is one of the videos that we had put on our channel, so which shows running of the MESA code. So this is something that everyone can access. So I just wanted to put it here. So you can put the initial conditions of the star that you are interested in, and it evolves accordingly and shows you the evolution of different parameters of that star and also along the HR diagram. So these are the different quantities that it is able to calculate. But so this is open. It is, as you can see, it's an open source software. So if anyone wants to tinker with it, so this is, I'm just putting out here. So we're talking about stellar evolution. So as you see, these are normal stars, the one on the main sequence, like sun-like stars, and even bigger stars or smaller stars. But eventually they come out of it. You see there is a very tiny or basically sparse region here where you can see some dots. Those are different types of stars, and those are what I've shown here as this white dwarf. These are dwarf stars, so they are very small, and usually because they are small, they give out less power because they have less surface area, but they are disjoint from this main. So this is what happens like after you leave the main sequence as you evolve. So you might end this evolution. We had written a particular blog with one of my colleagues, Bandhan. So if anyone is interested to see how this evolution takes place, what are the different ways and what exactly happens at the core of these stars. You can refer to this article. I have the link and the QR code here. So it is a very complex topic, but we have summarized it in a short accessible to everyone. So this is about stellar evolution of our usual main sequence stars. So this is the roughly the picture of what happens. So this is the our stellar life cycle. So we have this star forming nebula. So it's a gas, it's a cold gas which collapses due to gravity, and it basically cools efficiently, so it can collapse further. So such gravitational collapse leads to formation of our stars that we see in the sky. Star like that of the sun. So on the left we see sun-like star, but can also form stars which are massive. Massive in the sense they are roughly more than 10 times the mass of the sun. So the route taken by these two type of stars are sort of different. So sun-like stars usually go after they run out of fuel. Fuel by I mean the hydrogen burning in the core. So when it runs out of it, it becomes basically we go into higher phases like helium burning and so on. And how far we go depends on the mass of the star. So sun-like star then becomes like a red giant, and then once it runs out of fuel, it collapses because of gravity, and it basically collapses and then rebounds. So that leads, and basically all the outer material is shed off, leaving something at the core, at the center of it. That's a very dense core, because a lot of material has come together and pressed and basically crushed all this material. So this core is very dense, and that core ends up something that we call as white dwarf. Okay, if the star is massive, it undergoes a slightly different phase. It becomes a red supergiant. It's much bigger, and since the mass is higher, the explosion that takes place, like in the case of the nebula, is much higher. It gives out much more energy, and that results in supernova, where it's a similar process basically, where you have mass falling inwards, and then you end up with a dense core, and the rest of the mass is shed out in something called as, again, we get a nebula. So in case of massive stars, we end up at the core of such events, we end up having something that we call as neutron stars. These are again small objects, but are much more compact than white dwarfs, and the physics is fairly similar, but a lot of it is like the fundamental of it, the interior part of it is completely different. Okay, and another thing that can happen is like the gravity is too much for any matter to escape, and that results in black hole. So I've marked this here in blue because these are sort of the end stage. So what was shown in earlier talk, like stellar. So this is like the stellar graveyard. So this is after the star has run out of fuel and has reached its death. So it's called as a stellar graveyard. Yeah. So to give the idea of why we are calling them as compact, so this is sort of our solar system. So if this is the sun, these are the planets. This is our Earth here, and this is our sun sitting with some other stars. You see there are smaller stars, and we have much bigger stars, Sirius, and it goes on, keeps on getting bigger, right? So this is our sun, and comparatively, you can see the Earth is 100 times smaller in radius. So compact stars, like I told you about white dwarfs, neutron stars, and black holes. So white dwarfs are stars which have roughly the same mass as that of our sun, roughly, but the size, okay, I come. So we had also seen white dwarfs on the HR diagram, right? So this is our sun. This is the main sequence. The giants are on the upper right. So as you go on the upper right, you basically get bigger and bigger radius of the stars. On the opposite end, on the exactly opposite direction, we have white dwarfs. So that's why they are called as dwarfs. Why? Because the size is much smaller. The mass of white dwarfs is same as that roughly of the sun, but the size is that of the planet Earth. So we already saw that Earth is 100 times smaller in radius or a million times smaller in volume. So if you pack the mass of the sun in the size of the Earth, we get white dwarfs, and this is what makes it compact. That's why it is one of the compact object. Why it can sustain so much of mass? Sun is usually bigger, but if you're crushing it down such uh, small volumes, usually the your helium burning and all the thermonuclear fusion is unable to support the gravitational pressure. But the mechanism that happens under inside the white dwarf is completely different. So it is supported by something called as degeneracy pressure, or it's a quantum mechanical pressure, and in this case it's electron pressure. So you have electrons and they give out a quantum mechanical pressure, and that is what sustains. So you also have nuclei and you also have these electrons around, and the sea of electrons just pushes the strong gravitational field. So that is why we are able to sustain white dwarfs. There are other kind of dwarfs. So there are. So this was also discussed in the earlier talk by my sister. So there are brown dwarfs, white dwarfs, and black dwarfs. So brown dwarfs are basically failed stars. So they are not really stars. They are just like Jupiter-like planetary objects. So they are very hot, but and very massive, but their mass is not enough to start the fusion reaction, so they don't end up becoming stars. So those are brown dwarfs. So that's not a star. So there is white dwarf, which I just described right now, and there is black dwarfs, which is a term used to describe like when white dwarfs live, they give out energy. So they are constantly giving out energy. There's no fusion that is creating energy at the core. So they're basically cooling down, and as they cool down, they will become dimmer and dimmer, and written what we call as black dwarfs. They also have this mass limit of 1.4 solar mass. So you'll find that most of all the white dwarfs that we have cannot exceed this particular mass, because beyond that mass, so the electron pressure is unable to support the gravity. So talking about observations, we know there is an electromagnetic spectrum. So this is where we talk about we also talk about visible light, but there are other wavelengths with which we can observe. So usually we have telescopes in all these wavelengths. So right from radio waves, infrared, visible, and on the higher energy side we have ultraviolet, X-rays, and gamma rays. As we go to higher energy, we usually go to space telescopes. Radio telescopes, we'll find them on Earth. Visible, the higher altitude the better, and normally X-ray, gamma ray, all these telescopes are usually in space. So they probe different physical processes of the same objects. Yeah. So this is, for example, the Milky Way, one of the NASA's image, in different wavelength bands. So from radio, you can see there is infrared, then optical, X-ray, and gamma rays. Another one is I've put here, added up here, is the neutrino, Milky Way measured in neutrino. Neutrinos are particles. So this is a completely different observatory, but we are mapping the neutrinos coming from outer space. So this is what recently this neutrino background was imaged. This is the electromagnetic spectrum, and usually, so broadly speaking, these observations are divided into different types. So one here on the left hand, those are light curves. So it's basically timing. So you point your telescope, you basically measure the flux coming in, and you plot that flux as the time passes. So these are called as light curves. Same thing, you can do something called as Fourier transform and turn it into frequency base. So this is one type of observation. Another is spectrum. So where you point the telescope and take the spectrum. So across different wavelengths, we calculate what is the flux that we observe. And yeah. So and then there is also X-ray polarization. So this has polarization in general. In X-rays, this is sort of a frontier right now. So nowadays we are able to make the measurements of. We have electromagnetic waves, but in what plane are they oscillating? So each of these give different information about the sources. Another messenger that has come out recently, almost like we have been over 10 years now since the first discovery. It was predicted 100 years ago, but it is of the gravitational waves. So when these such compact objects, these are very specific to compact objects. So when they come nearby, or basically they orbit each other and they are about to merge, they give out, the gravitational field around them changes so much, and this change basically generates waves which travel outwards and also reach towards Earth. So this is one of the animation from ESO. So these gravitational waves can be detected using something called as gravitational wave detectors. So we have electromagnetic observations, we have gravitational wave observations, and we also have now neutrino observations, basically detecting the neutrinos coming from different directions. Each of these give complementary information about different objects. Gravitational waves are pretty much exclusive so far to compact objects, because gravitational waves require very strong gravitational fields to oscillate, and very strong fields are created only by compact objects. So when you put a large mass in small volume, this is where you get extreme gravitational fields, and that's why this gravitational waves gives us opens up a whole window to probe such compact objects. So they are probed using what we call as gravitational wave observatories. They are basically Michelson interferometer, like the one shown here. So you have lasers going on in bouncing in L shape, and they are combined together, and which produces a pattern. So here is an image of such an observatory in Livingston, and the map shows the different locations of current gravitational wave detectors. So LIGO India is something that is being proposed. So it is still underway. So it is being planned, and it will is planned in Maharashtra itself, in Aunda district. So that is something that is to be expected, and there are these other detectors as well. So these basically probe the gravitational waves, or basically the changes in gravitational field or motion of these compact objects. All right. Again, same like electromagnetic wave, we have a spectrum here. So depending on with what frequency those stars are going about each other, we can have time scales of milliseconds, seconds, hours, and even years. So depending on these, what frequency we need to probe, different types of gravitational waves detectors exist, and also different kinds of objects emit gravitational waves at different frequencies. So as you can see, at our frequency is basically reducing on the right hand side. So this is the ground-based experiment that I showed, the LIGO one. But if you want to go to higher timescales or lower frequency, you need to go to space. And at even longer timescales, you need to use some interesting techniques to map these gravitational waves. And the processes here, like for example, ground-based observator, we can observe black holes, and we can all observe neutron stars. But we cannot observe the earlier part of neutron stars, or we cannot observe, for example, the white dwarfs that we have been talking about. So for that, we need to go to space-based observatories. So space-based observatories, since the length is bigger, they can probe lower frequencies, which would be useful for white dwarfs. So right now we are not detecting any. We have mostly been focusing on more compact objects, but white dwarfs is something, this gravitational waves, if we get to space-based detectors, that is something, that window will open up to study the white dwarfs. So electromagnetic, to talk about the electromagnetic observations, so they are basically white dots, and they mostly shine in visible UV, and they appear as some galactic sources. But given, if you know the distance, so this is what is also done by the recent mission like Gaia. What it does, it's basically calculates the parallax. It does astrometry. So basically observing the object when Earth is at one location, and then 6 months later you go to the other side of the sun. So that is the standard way, and you take the observation. It appears shifted as compared to the background because the object is closer. So this is the parallax. This can be used to measure the distance, and in such a way you can find out these white dwarfs. Again, you can do the similar techniques. You can do observations like timing, where you observe the white dwarf over time. So what you can calculate is basically things like luminosity, how the luminosity is changing with time. It might be a variable star. You can measure based on the timing. If it's say in particular cases, you can measure the mass, and you can also, in case it is pulsating, you can also measure the pulsations of these stars. Again, spectrum is basically where you calculate the flux at different wavelengths. So this gives you complementary information. Spectra is usually rich in such observations. This gives us quantities like temperature, magnetic field. In cases, you can also derive mass and the size, radius of these objects. So it turns out that mostly the masses that we have seen is consistent with the Chandrasekhar limit, and the radius is that of the uh, our planet size, Earth. Okay. On gravitational wave front, as I discussed, so white dwarfs usually fall in the low frequency end, which we are not sensitive at the moment with the LIGO detectors, but there are detectors which are being planned in the millihertz and decihertz. So these are short frequencies like Lisa, and also there are a bunch of programs for decihertz like Decigo, Tiango, and even maybe on the Indian side. So these will be operational in space, and they can then, if these are like this is like the future of white dwarf astrophysics. So we'll be able to probe the binary evolution, things like the spin, the eccentricity of the orbits, and also understand the something called a supernova type 1a, which is related to white dwarfs. So when you have a white dwarf and it accretes mass, and that mass, when it's accreting, the mass of the star exceeds the Chandrasekhar limit, it basically explodes into a supernova with a constant luminosity, and that is used in other field of astrophysics, which is cosmology, to measure the distances to farther and farther objects and to study the universe. So this is also something we'll be able to probe once this window opens up. Uh, Unfortunately, nothing related to neutrinos, because there is no process that in white dwarfs that will lead to emission of neutrinos. But we also saw there are other compact objects. If we have the massive star, massive star like more than about 10 solar mass, it goes a different route and ends up in something called as neutron star and black holes. So this is the process, supernova. It leaves behind a nebula. It looks something like this. So when you undergo this phase, supernova, basically this is how it looks like. And at the core, so you most of the mass is given out, and that is called as a nebula, and at the core there is a central object which we call as neutron star or pulsar. So this is another set of, this is the same compact object, by the way, as was also uh, uh, discussed in the last presentation. So these are neutron stars, and we usually observe them in pulses, so pulses of light. So that's why they are also termed as pulsars. In this case, they are much more compact. We saw that white dwarfs are have the size of that of the Earth, but neutron stars have a size as that of a city. So city like Pune. So it's order of 10 kilometers. It's very much more compact and gives out much more gravitational waves and much more richer in physics. We can't even plot it on the HR diagram because the temperatures are like more than a million Kelvin or million degrees Celsius. So we are way out of this plot. And luminosity, talking about luminosity, it does not just give out optical or something. It shines across the electromagnetic spectrum. You will observe them in radio, all up to X-rays. So as I said, this is how you usually observe them. So they have been termed as pulsars. So it is sort of a lighthouse effect, which was also shown in the last talk. And you get pulse of light when this basically jet of light crosses our line of sight. So we get this pulse sort of a behavior. So if you point our radio telescopes towards these pulsars, so we get this pulsation. There are various types of pulsars. So there is one talk that my sister had given, and it is available on YouTube on our channel. So it's called an exhibition of pulsars. So I won't go into the details of what all types of pulsars are there. It's a huge topic. But if anyone is interested, you can refer to this talk where different types of pulsars are covered. Moreover, one more citizen science I wanted to point out is this astrosound. So Professor Catherine Kohlenberg, she had visited here. So she had talked about how these different pulses are basically turned into sounds. So even citizens are welcome to join the effort. So basically turning these pulses into sounds, and this has also been done for a lot of pulsars already. So you see, this is the one of the websites of Manchester University, and you'll see different pulsars. So these are different pulsars. You see the pulse profile in the image, and this you can basically convert to sound. So there's a list of um, pulsars, and you can go and check this out. You can basically listen to the pulses, and this is how you get the data essentially. This is how the data looks. This is also from my sister's slide. Uh, so this is how the pulses appear, and then you can do the analysis of these pulses to derive various uh, inferences for that particular object. So how you usually do it has to do with the scientific analysis, and one of the softwares uses HIA soft, high energy astrophysics software, and we also have a video on our channel describing how these pulses are used to derive the quantities related to the object. So this is something I also wanted to highlight. Um, yeah. So you see, this is one of the pulsars, SNX3, and you're showing the image of the pulse as it becomes brighter and dimmer. This can be done in X-rays as well. So this has been done for a bunch of pulsars now. So what happens is, when you have matter being accreted onto a pulsar, so this matter goes and hits the neutron star and creates some hotspots, like you can see on the bottom left, and can be of different shapes. And this different shapes leads to different sort of pulse, the basically pulse shape. And from this pulse shape, you can basically derive the shape of this hotspot. You can derive a multiple quantities like I've listed here. You can estimate the radius. You can estimate the temperature of the surface of that star. Another different things, you can measure mass from pulses coming from radio waves. You can measure the period, the spin period. From there, you can also derive how fast it is slowing down. That can be also used to calculate the age of the star. The temperature, if you observe over time, you can also map the cooling techniques to find the magnetic field, probing the atmosphere of the neutron star. And also timing also gives you, we have found this events called as glitches. Glitches is where you have this pulsar and suddenly it starts spinning up. So this is basically the frequency as a function of time. So it's usually spinning down. Suddenly you see a spin up, and then again it starts spinning down. So all of this has to do with the interior, like glitches particularly has to do with the interior. Some things like the temperature and atmosphere, they are concerning the atmosphere or the exterior of the star. Glitches, for example, has to do with the interior. The mass radius relationship has to do with the interior. You see on the top left, I've shown mass radius plots. So these comes from different X-ray observations of different pulsars. So you can make such observations and derive mass and radius. You can get such plots even using gravitational waves. So gravitational waves, as I shown, when you have these pulsars or neutron stars going around each other, they give out gravitational wave. They also merge, as you see here on bottom right. Two neutron stars can come together. They can capture each other due to their gravitational field. They orbit each other, and as they orbit, they give out gravitational waves. And because of this emission of gravitational waves, their orbit shrinks, and at some point they will merge. So they'll merge, as in they'll hit each other, and that will be again a huge explosion. So this event, if we can observe in again gravitational wave, that gives us a lot of information about these compact objects. So there are different ways in which you can, as I said here, I talked about this in spiral, merger, and post merger is when those two stars basically get together. So that is the one I was talking. Also, if neutron stars has mountains, has deformations, right? There are different mechanisms which again can lead to emission of gravitational waves. Another thing is oscillations. So oscillations, if you have this neutron star, if you perturb it or something comes and gives it a push, like some other object comes nearby and sets in, or during the formation itself, it doesn't settle. So this star can start oscillating, like you see in the GIF here. So this star can oscillate. This happens even on Earth. For example, earthquakes or any stellar quakes is basically your star or your astronomical object is being disturbed. That also gives out gravitational waves, but they are very weak. But in case of neutron stars, since it's very compact, they give out a lot of emission and something that can be measured. Such detection of gravitational waves is something that this is how we observe it on the bottom right. You see, we get a waveform from this Michelson interferometer, and from this waveform we can derive certain quantities like the mass of the star. Okay, another quantity is tidal deformability. It basically tells you how easily it can be deformed. Sorry, there should be an arrow. So from the tidal deformability, we can also infer the radius of that object. And so far, we have had one good observation, which is consistent, and we find the radius of about 10 kilometers again. We can calculate the spin, which is also possible from radio observations directly, but this gives you an independent handle. You can also observe different effects like tidal heating, which has to do with how these objects absorb your if they take in gravitational energy. So it is a parameter which basically is helpful in deriving some fundamental physics as to what that object is made of. So these are all the things that you can probe using gravitational waves. And the third messenger is the neutrinos. Unfortunately, we do not have many events. Actually, we only have one event, which is long back, supernova 1987, where two independent observations of neutrino bursts were measured and it was mapped to a supernova event. So when you have this supernova, you have the earlier supergiant. It runs out of fuel, and the matter goes in. You have the supernova. The outer mass is shed away, but the inner core is basically very, very, very massive, and it's very compact. So matter is crushed to very small volumes. And what happens is that the atomic structure also breaks down. So what happens now, your neutrons and protons, which are inside the nucleus usually, they also those are the particles which start mattering, and neutrons and proton reaction takes place, which lead to emission of neutrinos. And this emission of neutrinos comes from the entire volume of the star. For example, the electromagnetic observations that we've been talking about, they only come from the surface because light is emitted from the surface. We don't get directly from the interior. Gravitational waves and neutrinos, these are the two messengers, astrophysical messengers, which can be given out from inside the object as well. So neutrinos can be produced at the core of neutron stars, and they will come out without interacting, freely stream out and reach our detectors. So gravitational waves and neutrinos are the way where you can probe the interior of these stars, of neutron stars in particular. But we are again at a very early stage of it. So these are some of this is the IceCube observatory, which also helped in mapping the neutrino background. And this is Super Kameganda. And there are more neutrino projects proposed because they're important, because we still have only one observation. And if we could open up this window of neutrino detection, we can do much more physics, especially with the interior of such objects. Right. So this is one of the just a Venn diagram of different observations. Gravitational wave, electromagnetic, and neutrino is one of the white papers recently published, and I co-authored here for the neutrino part. So it shows what different physics can be done with the intersection of different messengers. So why multi-messenger observations are important? Why two different observations? They are not disjoint. So when two observations come in, you can probe a lot of things. So this is mostly talking about high energy events and neutron stars, which is one of our compact objects. So this is the future, as I told, the neutrinos, the space-based detectors, and some new space telescopes which are coming up, and The Einstein telescope and Cosmic Explorer are again next generation gravitational wave detectors, which will make observations of neutron stars more frequent. As I was talking, this all comes under extreme physics. This is also shown in the last my sister's talk. So these pulsars, this is one of the most extreme and most compact objects, physical objects that we have in the entire universe. We had given a talk of this popular science talk. Basically, it has extreme gravity, matter, density, pressure, magnetic field. It has all of rich physics. You'll find material science, condensed matter physics like superfluidity, superconductivity, what is everything inside neutron stars itself. In this case, it is balanced by neutron pressure instead of electron pressure in case of white dwarfs, and the interior of the stars are still unknown. So it's like an open question, and that's why these multi-messenger observations at this point are crucial. What happens inside? There is a bunch of things. You can have different types of particles, again relating to particle physics. You can have hyperons, things, and so on. One more interesting avenue is these neutrons and protons are further made up of quarks, so that can lead to hybrid stars where you have a quark core or even quark star completely. That is another compact object, which is basically an alternative candidate to the physical model of these pulsars. Like we have neutron stars, we have these quark stars, which are again one of the compact object. So this is I was talking to neutron star. If you put a quark core, so it's basically quark matter, you can have a hybrid star, or the entire star made up of quarks, you can have quark star. You can further have in this compact stars, you can have mixture of dark matter, which is an entire field in itself. But at the compact scales, because the gravity is strong, you can have admixture of dark matter as well. So you have this dark matter admixed stars. So this compact stars and their observations can again be used to probe something completely different, which has to do with dark matter. As I said, so when they merge, it again creates a huge explosion, so which is usually called as kilonova. This gives out gravitational waves, and yeah, so a lot of matter is ejected. It is observed in electromagnetic as well as gravitational waves. You also have a lot of neutrino processes going on, nucleosynthesis, and they're also related to one of the astrophysical events that which are usually termed as gamma ray burst, usually the short gamma ray burst. So it's a spike in gamma rays. So this is also associated with these compact stellar events. And the last one, I'm talking about the black holes. So black hole is, so I said neutron star is the most compact, but actually it's the black hole. But the thing is, black hole, we don't know any physics of it. It's not an object as such. It is just a volume, or basically a space beyond which we cannot look. So we don't know what it is made up of, what physics goes in it. So neutron star are the most compact physical objects, as we call it. Black hole, you might have heard about it. It's basically a singularity, and the gravity is so strong that even light is not able to escape from inside this particular sphere, which we the ball that we see, which we call as the Schwarzschild radius, or the basically event horizon, or the surface of the black hole. Any radiation that we see is only coming from outside this black hole region. So the ways to probe this are usually from, if you talk about electromagnetic point of view, so one is black hole shadow. What you see is basically it has to do with accretion. If it is accreting matter, the matter around the black hole heats up, and that matter which has heated up, it basically shines. So you can point your telescopes and observe these black holes, and what you will see, basically you will see the accretion disk and a hole in the center where the light is missing. So this is how you can say, okay, there is one dark patch at the center. This is one of the famous black hole images, which has been recently released by the Events Horizon Telescope, the radio telescope. You see that there is a shadow region, which is called as the black hole shadow, or just the shadow, and then you see the accretion. So this is one way you can probe, okay, whether there is a black hole there, and you can also probe its properties. Another way is stellar orbits, because there are a lot of stars. Say there is a black hole at the center, so the stars that are orbiting them, we can map them out, and these orbits will also precess. So observing these orbits of other stars, which are usually visible in electromagnetic spectrum, we can talk about what exists at the center of it. We can talk about how compact it is. We can, even though we cannot see whatever there is at the center, because that's the thing about black holes. We cannot directly see the black hole. We need something around it. This is the way people usually probe black holes using electromagnetic waves. And this is the second way is gravitational wave, because black hole has mass. It is very compact. It again gives out gravitational waves, especially when you have two black holes going around each other. So you won't see any matter. You won't see any light coming from there. So it's as good as a dark patch on the sky. But if you have gravitational wave detectors turned on, you will we do find, I mean, that there are gravitational waves coming from this dark patch. So two black holes might merge to give a black hole of higher mass, and again we can get a waveform of this merger event, and this gives us different properties of the black holes. These are very important because black holes are extremely difficult to detect otherwise, because we cannot see them. So but thanks to gravitational waves, we can measure things like the masses of these black holes. We can measure the spin at which they are spinning. If we observe enough such events, we can also map out the population of black holes and how they are dispersed across our universe. We can talk about the evolution of black hole over the period of the universe. And notice we have been talking about this dark patch. We still are not completely 100% sure whether these are black holes. We just know that it looks like a black hole. There is something that the light cannot escape, and there is matter around it. It could be anything. It need not be black hole. I'll come to that later. Basically, this waveform also tests our theories. So theory of general relativity is the state-of-the-art theory of gravity. And this gravitational waves is also predicted by that theory, and whether what you observe and what the theory predicts matches. So these tests are also done using gravitational wave physics of these compact objects, in particular black holes. So you can improve your theory just like Newton's laws work, but they are not the correct description as far as we know right now, because it fails certain tests. So if there are any tests, so this is what also people find out using black holes. Maybe there is a higher theory. So this is how you can prove fundamental physics using black holes. Just like in case of neutron stars, you could probe a lot of rich physics like condensed matter physics. You can do particle physics, right? Neutrino physics. This is something you can do using black holes. There are certain limitations, as we said, that we don't know if they are necessarily black holes. There's this recent news article, early universes, little red dots, is something that has been observed by the recent JWST telescope, but it is not. There's no still consensus about what it is. So there's still confusion, and there is one of the leading explanation that it might be like these might be related to black holes in the very early universe, right? So there are certain problems, certain fundamental physics problems related to entropy. So there is this information loss paradox about black holes, whether you can have this singularity and not have an event horizon, whether that is allowed. So there's this conjecture which says you cannot have such singularities existing without a horizon. There are alternative solutions of stars, like black hole is one of the stars. There are other types of stars which I'll come to soon, which also exist, and which will also explain things like this black hole, like this shadow, which can also create this shadow. It can also have a dark patch and a shadow region. And there are also an open problem of dark matter, which again leads to certain other types of compact objects, even black holes. So a part of your black hole population can explain the missing matter in the universe. But so far from what we know, that is not the case. So we also need explanations for dark matter. So we come to something called as exotic objects. So these are again compact objects. But from now on, so far whatever I've shown is fairly established. So these are mostly conjectures. So like we do not have any direct evidence of these yet, but this is something that people are trying to find. These are called as horizonless compact objects. Like you have black hole, it has no horizon, but it may not have a horizon. They're also called as exotic compact objects because they are like exotic solutions of existing theories which have not been ruled out, and people are still testing whether the observations are being consistent with this, and some are and some still are consistent, right? There are ultra compact objects, or also called as black hole mimickers. So there's a host, like long list of stars like grava stars. It's basically like a black hole, but you have some energy inside it, like dark energy, which pushes the matter, and all the matter is confined to a shell. The things called boson stars, that as I like saying, there's something called as anisotropic stars, where you have stars where pressure in the radial direction, tangential direction is different, and they can form even more compact solutions than neutron stars, but less than black hole. There are fuzzballs. These are like modified gravity solutions. So maybe there are modification of gravity, which also explains dark matter and modifies your general theory of relativity. And these have solutions like fuzzballs, which are still feasible. And these are other ones like wormholes, which people talk about. So we do not have any handle on these observational handle on these yet. These are sort of things that people are trying to understand. And these, since these are all dark objects, all of the physics that can be probed has to do with how the horizon or the surface of these objects appear. And since they are compact, these are almost exclusively can be only exclusively probed by gravitational waves. So no, in most of the cases, no electromagnetic observations are going to help. So I've just put a picture of the PhD hat which my supervisor had made. You can see the picture of Zuki. He had discussed or introduced this dark matter concept, and interestingly, he's also the one who had predicted neutron stars. So, and both of them are something that people are scratching their heads about today, and we fairly believe that they exist. So this has to do with other type of compact objects which are still conjectured, and I can talk about them in detail if anyone has questions. But there's a sort of class. Basically, you have some exotic particles, and it forms a compact object or solution in space, and does not interact with light. So, for example, like boson star, here I've shown a web diagram. So, if you talk about boson stars, it's basically a star made up of bosonic particles. This is a particular integer spin particles in particle physics. And just for boson stars, you can see there are so many possible. So if you go to, depending on how they interact, you can have massive boson star, mini boson star, quartic, sixth order, and so on. So it's a huge field in itself. And you can compare how these boson star images would compare with black hole. For example, here on the right, the upper row is basically a image of black hole if it has an accretion region. But you can repeat the same. The second row is the same thing but with a rotating black hole. And the next, the third and the fourth row is basically the same thing with matter around it. Sorry, there's some disturbance. Okay. So basically, you see, depending on how you describe these objects, these can look similar. This can look like the black hole image. So you can fit a similar looking object, explain similar object using something called as boson stars. So these are still not ruled out, and this is one of another compact object that may exist in the universe. So that was it about compact stars. So I just wanted to leave with something that I saw on the AAA website, that the members are involved with astrophotography. So there are some astrophoto events that I know. So LIGO India, the gravitational wave science collaboration, also conducts astrophotography contests. There is another one, Global Astrophotography Campaign, which is going on by the International Astronomical Union. This is something I wanted to just highlight. And I was also being asked about some citizen science projects. So there's this website called Zooniverse, which I wanted to highlight. So Zooniverse has a lot of projects, not just astrophysics, but general science projects. And you can also go under their physics or space, and you see a bunch of programs or projects which are going on. You can also see Gravity Wave Zoo, that has when anyone who is interested in contributing to science from their home can participate and help scientists with the gravitational wave astrophysics, for example. So this is what I wanted to highlight from citizen science point of view as well. So that is it from my side. So that was the compact stellar zoo of what all exists on the compact scales. So thank you.
Thank you, Dr. Swarnim, for the wonderful talk. We are open for question answer sessions. Anybody has any particular questions related to the topic can please raise their hand and take opportunity to ask the question. Ravi, you want to take up? There is a question from one of the students in a chat box, WhatsApp chat, where he is asking what uh, is the nearest compact star object would be from the Earth.
Sorry, what the
Nearest compact object
compact object?
from the Earth.
So yeah, so most of these compact objects that I have talked about, so they are present in our galaxies as well as extragalactic. So we cannot resolve these sources as I talked about different electromagnetic observations. One more is basically imaging. So we don't do imaging here in this case, except for some supermassive black holes. So black holes, whatever we have observed, most of them are this extragalactic. So we are observing merger of black holes in different galaxies. So they are not even in our galaxy. So they are like uh, megaparsecs away, or basically 10 raised to 6 light years away from us in different galaxies. So even the image of black hole that we have done, that is from N31, a different uh, your different galaxies, and Sagittarius A, so the center of our galaxy. So that is one supermassive black hole that we have at the center. So that is around 10 kiloparsecs away, roughly 8 kiloparsecs away, which is about 10 raised to 4 light years. Apart from this, white dwarfs and neutron stars. So neutron stars we have about I think 3000 roughly, which we have mapped. So there are different repositories, mostly from radio observations. So there those and white dwarfs. So those we find completely in our neighborhood. So the closer the better, because uh, the closer they are detectable, and the ones that are far away in our own Milky Way, so those we won't be able to detect. So what we usually observe is one in our neighborhood of Earth, and they can be basically, I don't have the exact number for the nearest one, if but basically you'll have it in multiple parsecs and kiloparsec scales from us.
I think nearest to us known is basically Sagittarius A, probably 26,000 light years away. What is mostly studied and observed, I mean, radio.
Yeah, that would be for the black hole.
Yeah.
Yeah. Yes.
Another question, I think one question is there in chat from Sarita, that what is the black hole made of?
Okay. So it's a yeah. I think a lot of people have this question. So we can talk about what white dwarfs are made of. We can talk about what neutron stars are made of, because there is material and it has a density and has a surface. But black hole is an object where you cannot sustain matter in gravitational equilibrium. In equilibrium, basically, you cannot have pressure in this matter enough to sustain that extreme gravity. So that is when you form black holes. So what happens when you cannot sustain the pressure from gravity? The matter keeps falling in, right? So when the matter keeps falling in, what happens? So what we understand is the matter keeps falling in. It becomes more compact. It basically becomes more compact than the event horizon itself. So you get a sphere outside from within which you cannot get any light out, and the matter goes in, and since it cannot support any, so and as the matter falls in, the gravity becomes even stronger. So it's like a runaway thing. So you cannot stop So what we understand on how it is usually modeled is basically all the mass that existed that was falling in goes and sits at the center. Like you get a singularity. It's not that there is some object at the center. It's just a singularity. It's like a point. So that's how you mathematically model it. So you get singularity at the center. We don't know what happens in between that and the event horizon. We don't know what happens at the singularity itself, because even your usual laws of mechanics or physics break down at such tiny scales. So that is where you need to resort to other theories, like you need to combine gravity with your quantum physics and so on, which is still a topic of research. So we don't know what's there inside. We just, from what we know, is that the matter goes and sits, becomes a singularity, and that is how we model. So that's why I said I don't call it the most compact physical object in the universe. It is a singularity directly. So we don't know what that exactly is, physically speaking, except for what happens outside the horizon.
Yeah. Uh, thank you, Swarnim.
Yeah.
We have a question from Hemant Kumar sir.
Yes.
Over to you, Hemant sir. Hemant sir, you can ask the question. Yeah, you're on mute. Hemant sir, you are not audible if you are speaking. Or you can type the
Maybe.
question in chat.
Yeah. Maybe in the chat.
Okay, meanwhile, Hemant sir comes back with his question. I think one more. Who is one more? Ashwin, you want to take up? Ashwin,
Okay,
please go
Mangesh,
ahead.
sir. I can, I think maybe his mic is turned off.
Yeah, he unmuted, but unfortunately, I don't know. We are not able to hear him. Yeah, Hemant sir has put up the question. What is the most acceptable method to record the position of a black hole in the sky?
What is the most acceptable method for positioning? What about, am I audible?
Yeah, yeah.
Yeah. So one thing I talked about is related to this radio observations. So, but those are restricted to supermassive black holes. We already know the centers, like where roughly these are supposed to lie. This also comes from the stellar orbits. So we see that these stars are moving around one particular point. So that is where that black hole would be sitting. So if you focus there enough, you can see. So this basically pinpoints to a very small volume, and that when you focus, you can see this accretion disk. That is how you know the position. Apart from that, this that is from electromagnetic observation, so that is fairly straightforward. But when it comes to gravitational waves, so everything has to do with the waveform that you observe in your detectors. So you have these black holes going around each other somewhere in the sky, and those are merging, and you get a waveform. Now the waveform that you get, of course, depends on the properties that I have mentioned here, like the mass, spin, right? Position in the sky, detectors, how far it is, right? At what point does it merge? So these are all, so I have not listed them here. So these are the properties intrinsic to the object that I just mentioned here, like mass, spin. But there are other properties like location, the sky location, the inclination, at what angle it is, right, the distance, and so on, which also go in the analysis and also the generation of this waveform that you actually detect. So from the waveform, you can, apart from this, also the inclination, the distance, one of these particular black holes. But mind that given the current sensitivity and the fact that we only have a couple of detectors, the localization is not that good at the moment. So we can only talk about a certain patch in the sky, and we say okay, it's roughly there, but that patch of the sky contains lot of galaxies itself. So only in very few cases where the event is very clear, the signal is very clear, we are able to pinpoint it to a particular galaxy. we have no idea at the moment, at least pinpointing it to a particular host galaxy. Yeah.
Okay. Thank you, Hemant sir. One more question from a student. You spoke about earlier the life cycle of stars, where you demonstrated about the cycle starting from the cloud and then eventually depending upon the mass and all, and eventually the white dwarf or brown dwarf and neutron star or black hole. So student is asking, what is the end of black hole? I mean, what happens? I mean, is it existing forever, the black hole, or there is something maybe today visibly not available, but probably mathematically there is
Yeah.
consider.
Yeah. So it's interesting question. It has also to do with this information loss paradox that I talk about. What happens is that black holes were long thought to be like the final stage, so they just sit there. But there is this uh, physical process which is proposed by Stephen Hawking, so which we now call as a Hawking radiation. We know that a black hole does not just sit quiet. So when you apply these when you basically apply quantum mechanics at the surface of these black holes. So what happens? It can lead to certain processes which can effectively take out mass from the black hole. So what happens? This is what is called as a black hole evaporation. So the black hole is constantly radiating. It also has a temperature. It basically gives out. It is. It gives us this Hawking radiation, and as it gives out this energy has been taken away from the mass of the black hole. So this takes a lot of time. So this happens at a. So basically, smaller black holes evaporate quickly. So that is why we are not able to see. Talk about any black holes, so they would have evaporated by now. There is a particular mass range above which only we can observe these black holes. So what happens is this mass of this goes on decreasing, and the radius of the star also depends on, it scales with mass. So it is directly proportional. So as mass goes down, the radius also goes down. So this is called, this process, the black hole evaporation. For massive stars that we talk about, the time scale is very high for such evaporation, so that we still see them, and we will keep seeing them. But for smaller stars which we have not detected, black holes which we have not detected yet, so this should be basically, this black hole keeps on evaporating, its mass goes on and its radius goes on, and everything basically it completely evaporates beyond a point. And that's why it has, I said, it has to do with information paradox. Basically, the entire information of what matter had gone into this black hole is basically completely lost in radiation, which is like perfectly random radiation, in basic terms. So you cannot make out anything of what was there inside, or like you do not get any information about what happened inside. But basically, over time, these can evaporate. And
Thank you. Ashwin, you have a question?
Yes, Mangesh sir.
Yeah, please go ahead.
So, did you study the GW 17081 event? And if so, can you shed some light on what you learned from the merger? And was there any signature of a black hole being formed at the end of the merger?
yeah, so they usually relate it. Hello.
Yeah, go ahead, Praveen.
Yeah. So usually, so this event 17 this is one of the only events that we have clearly observed for double neutron star, and with a good SNR. So we have measured the what we call as the inspiral phase of it. From the waveform, we can derive certain quantities, like we know the mass of how, depending on how the frequency evolves. So we know the waveform. So from there, we can derive the mass. So like the collaboration at that time, the analysis derive the mass of these objects. So the another quantity that I talked about, the tidal deformability. So that was also been measured, but that is a very loose measurement. Loose measurement is it has a large error bar. So at best we can say what is what we usually say is we put a upper limit on this tidal deformability.
Okay.
So we know that the deformability of this object is not beyond a certain limit. I think I had a plot. Yeah. So you see the plot on the top right. So this is lambda
Yeah.
term has to do with the deformability. Lambda 1, lambda 2 is basically of the two components of the binary. So you see the dark patch is where it's the most likely measurement exists. So only at the lower lambdas is what we have uh, below basically, and there is no strict cutoff at the lower limit. But basically there is a tidal deformity. It's a non-zero one. So we know it is a neutron star again because the tidal deformity is non-zero. In case of black hole, it turns out to be zero. This is another information that we have. Using tidal deformability, we know what neutron star models, how they are made up, what they are made up of. So using this information as well as the physics of the neutron stars, what has also been derived is the radius of this object. So again, using this measurement, the lambda measurement, and knowing the mass as well, this information is then combined with the neutron star physics to also talk about the radius. So we also know the radius of what neutron stars should be. So there are the different things that we know from this particular event.
Thanks. Ashwin, you have anything to ask further?
Thank you. Can I ask one more question?
Yeah.
Please.
Up to what point during the merger can you observe with the gravitational waves? Can you actually see the final merger, or
So yeah, so it depends on the mass. It depends on the mass of the objects that are merging, right? For example, in case of neutron stars, it's difficult to observe the actual merger because they are compact and small. Their actual the frequency at which they orbit each other at the time of merger is very high. It goes in kilohertz. Like so, roughly what we observe right now is between 100 to 500 to 100 to 1000 hertz with the current detectors. So if you are talking about these compact objects, or even if you talk about like smaller black holes that we usually observe, they go in kilohertz. In the current band, what we today can see is basically black holes of tens of solar mass orders, right?
okay?
So their mergers is what falls within our current LIGO band. If you want to go to even massive stars, we'll have to or massive stars or basically less compact, like in the case of white dwarfs, like we discussed, or even in the initial stages, if you want to see neutron stars like much before the merger. So those frequencies are shorter than those go in short, like lower frequency bands like decihertz and millihertz. So these are the gravitational wave detectors that need to be put in space because they are we need very long lengths, and these are at the stage of proposal at the moment. And when we talk about the supermassive black holes, so those are like much bigger. And if you're talking about the merger of these black holes, their frequencies go in microhertz or even nanohertz. So there are other techniques which I specifically didn't discuss, and that also involves pulsars, interestingly. So basically the timing of pulsars, of known pulsars just around the Earth. So based on how these timings are affected, we can measure gravitational waves of very low frequencies that are passing through the entire region around the Earth and also through the Earth. So those frequencies are in nanohertz. So 10 raised to minus 9 7 hertz. So those are associated with large objects like supermassive black holes that we talk about. They're much bigger, like 10 to the power 6, 10 to the power 9 solar masses. They're like completely different beasts. So those we have that is done by using pulsar timing array, and we have some observations so far, but still a long way to go.
Okay, thank you very much.
Yes.
Thank you. Thank you, Ashwin. Anybody has any other question, or we are good to conclude today's session? Thank you, Hemant sir, for encouraging the words. Thank you, Dr. Swarnim Shirke, for giving this or delivering the outstanding AstroTalk compact stellar zoo. Your engaging presentation made us the complex concept of white dwarfs, black holes, and multi-messenger astronomy easy to understand and truly fascinating for us to understand. Your passion for astronomy inspired students, members, and stays enthusiastic to explore the wonders of universe with great curiosity. Once again, on behalf of Amateur Astronomers Association Bombay, I thank you for your valuable time and insightful knowledge and wonderful interaction. We definitely look forward to welcome you again for many more such inspiration sessions. Thank you very much and have a good day. Thank you.
Thank you everyone. Thank you for having me for this talk.
Thank you, sir. Thank you very much.
Yes.